Oh, there was one that your colleague helped me with earlier. It's now gone.
No, that's right.
Of course.
Okay. Our last speaker, Michael Benedikt.
Can you hear me? Most of you have heard about this notion of great thoughts time. We were discussing it with Wolfgang at lunch. The idea is you have impose a discipline on Friday afternoons after lunch. You only think about great thoughts. And I had the notion that I, and also with you, I think great thoughts about the foundations of data interfaces, about radically rethinking the notion of logical interface to data. Friday afternoon. It's Thursday. I'm not Richard Hamming, so I need some kind of warm-up where I'm thinking maybe some trivial thoughts, some maybe mediocre thoughts, as a kind of stretching exercise. And so that's what this talk is. I'm going to go over some projects which I think will maybe give the notion of the goal of rethinking interfaces to data. And that will prime the pump for, not even for questions. I won't be at peak great thoughts time by question time, but maybe by tomorrow afternoon, I'll be ready for great thoughts. So first I have to explain what I mean by an interface to data, because this is what I want to rethink. Well, an interface to data in general is something you have a class of users and you want to restrict, you have some source data, and you want to restrict the kind of queries for that class of users that they can answer. So I'll give some examples of this later. This is not what you normally think of. Maybe this is not even the best way to think of an interface. You normally think of an interface as maybe a layer, like an ontology layer, where you have a different vocabulary, a different data model, or a different API that users have. But from the point of view of expressiveness, this is, I think, one way to think of these interfaces. The bottom line of whatever you give to users, restricted language, different data model, is that there's a limit on what they can ask to the source data. And you can begin to compare different interfaces this way. One person uses this vocabulary, one uses this data model, one uses this semantics. If you want to compare them, you'd compare based on what class of queries the user can extract, what information they can extract from the source database. And we'll also look at this in the setting of multiple databases, autonomous, distributed over the world. Then an interface will be a restriction on what users can ask to the global database, the union of the sources, but it will have to be compatible with this notion of autonomy. It should be something that factors into an interface at each source. So there'll be examples later, but the canonical example is traditional database views, say SQL views. This is an interface at least based logically on making some derived data available. So you say, well, here class of users, here's the stuff that you're able to see. Go wild with any query that you can do that only uses this data. That's a traditional view database. Abstractly, you can think of a view-based databases. You have some function on the source instance, or in the case of distributed views, on the source instances. And this function extracts some data. That's the stuff that a user can see. Any query that only uses that stuff or is answerable based on that stuff is the restriction on queries. So I'll use some terminology in the distributed case. I'll talk about distributed views. A distributed view is just, on every local source, I have some derived data that I at least logically export from that local source. Okay, so views can be in these arbitrary functions. We'll be interested often in classes of views, like say CQ views. A conjunctive query D view is at every local source I have a conjunctive query over the atoms known to that source. That's what that local data source is exporting. So the idea of this great thoughts exercise is to try and go beyond views. And lots of people have gone there before. And you can begin to think of lots of mechanisms that have been proposed. I mentioned some of them. Access patterns. This is another way of restricting what a class of users can see that's not derived data. You say, okay, you need to give this a value here to access this data in this functional API that's different from derived data. And then, so that's something that has been studied in the database literature. Alan Nash and his colleagues, people at Stanford, Chen Li and Edward Chang, Deutschnaschen literature. Views with access patterns, something that hasn't gotten that much study. Nash, again, and his colleagues, Antoine and some colleagues at Telecom studied this. You say you have logically some derived data, but you restrict access through access method disciplines. Various data exchange, virtual data integration mechanisms. There's lots and lots of them in the history of databases. These can be thought of from the point of view as trying to get beyond views. There's an interesting formalism from Countess Deutsch and Anose, query specification pattern language, something like that, where you use a restriction, an automaton running over the syntax tree. And you say, here are a class of users, here are the things that you're allowed to see. Here's a number of queries. This is going beyond views. They talk about this as exporting an infinite class of views. And so this is the kind of thing I'd like to look at. I mean, I'll talk about two projects, one from a couple years ago with Pierre Louis Jacquet and Effie Samora, and another that's current work with Udi Rashkovsky at Oxford that are in this space of how do we get mechanisms that go beyond views. Okay, the first kind of mechanism is this first project. It's based on the notion of minimally informative query answering. The notion here is we specify a set of queries. We call them in the paper utility queries. These are the things that we want the user to answer. But we don't want to give a mechanism that just says you can only ask these 5 queries. We want something more robust. So what we say is, well, let's give out the minimally informative traditional views within a class that support these queries. I'll give an example in a slide. So here, this is something we've also discussed extensively at lunch. Dogstool versus Simons. Computer science conference centers, very theory friendly. They both have programs with different participants. Many people here have gone to both. And they have both autonomous data stores that store the names of participants, which program, which year. And they get together and they say, we're going to create an interface. And we want our interfaces to support some queries that span the sources. Like, are there researchers who are attending both programs in the same year? We can write this as a conjunctive query over the union of the schemas. So it's a join between Simon's participant and Dogstool's participant. And we want a mechanism that will support this query, but give out the minimal information among distributed views that will support this join. So we have to formalize this notion of what it means to support a query and what minimal information means. And I'm coming late to this program, but I've seen that a recurrent theme in this program is information and information theory and Shannon, relative information. We're not going to use any of that. We're going to do something less quantitative that I think is one of the things I'd like to advertise. It's Segoffin and Vianu's notion of determinacy. Sometimes in some of Dan and Paris's papers, they emphasize information theoretic determinacy. So it has a similar feel. What is determinacy? You have a query and you have a bunch of views. You say the query is determined by views if any database, 2 databases that agree on the view agree on the query. A very simple definition. Another way to think of this is that the query output is a function of the view output. So we'll say that a distributed view supports a query if the query is determined by the view. But the way you want to think of determinacy is, information theoretically. It says, well, these views contain all the information you need for Q, or these views have more information than Q has. And the information theoretic notion is you don't care about the computation, how complex it is to reconstruct Q from V1 through Vt. Who cares? V1 through Vt have enough information to answer Q. And we'll formalize the notion that the views are minimally informative, again, using Segoffin and Vianu's notion of determinacy. we say a distributed view is minimally informative, supporting Q within a class of queries C if the view supports the query, using determinacy. Q is a function of the views. The view has to be based on queries in C, and any other distributed view V prime that uses queries from C, it has more information. That means that other view V prime determines each view in V. So remember the notion of determinacy. If V prime determines each view in V, that somehow says V prime has more information than each view in V. And so this is the natural way. If you accept determinacy as the notion of information capacity of a view, this is the natural way to say that these views are minimal information. So let's go to Simons and Dodgetool. At least in our minds, go to Simons and Dodgetool simultaneously. They wanted to support this interface that supports this join and give the minimal information that does this. It's pretty obvious intuitively what the minimal information you need to support this query is. You need to know, Simons needs to reveal the name and the year to support this join, because name and year are the join variables, right? They cross the join. Dodgetool also has to reveal the name and year. And so what Simons should do is they should publish the projection on name and year. And Dodgetool should do the same. Give the projection on name and year. Intuitively, that's the minimal information. And in our formalism using determinacy, that's the minimal information. Does this make sense?
Yep. The minimum information is just true or false. The answer to the query.
It's the minimal, it's a static notion. It's minimal. This is not instance determinacy. It's determinacy over all instances. So that back in our notion of determinacy, it's over all D1, D and D prime. So it's a static, it's a data independent notion.
Okay.
So on a given instance, of course, I could say, the answer is true or false and so on. But the minimal information views are views that will have the minimal information defined in terms of instance independent determinism.
But I can play the same game. You give me your instance, I'm going to compute the view, which is just the answer to your query.
These are autonomous data sources. These views, the distributed views, are views at each source. So I can't go, Simons is not allowed at data time, at query time, to go to Dodgetool and say, tell me what's going on, and then export the data. That's this notion of distributed view says that each source has to do its own thing.
This makes a lot of sense. Thank you.
Yeah, but if I may, so
yeah.
I mean, it seems in this particular context you want to be as restrictive as possible, right? So the instance level seems to be what you want to go into, and there could be something like a zero knowledge proof like thing that's in a protocol between Simons and Dodgetool, right?
Yeah, I talk. So the question about what happens. So okay, the first thing is, so of course, if you do instance dependent things here, there's also some questions about these epistemic paradoxes. You say, no, I can't answer your query because that would be giving out too much information. But okay, so here there's a question about whether other mechanisms could do more than these views, which is a question I'll get to.
Crypto people have looked at, right? I mean, so
Well, crypto people have looked at it, and actually, well, I've looked at it too in a couple slides. Okay, what's an example of our results? I won't, of course, completely address your question in a couple slides, but maybe it'll be more clear. So in this paper, one of the results says you take any utility query, not necessarily conjunctive query on an SQL, arbitrary function on the global schema. Then these minimum informative D views exist. I'll say a little bit more about what they look like in a few slides. For CQ utility queries, they're expressible as traditional views in relational algebra. And we show that the same holds in the presence of integrity constraints on each local source, like TGDs, EGDs. So you always have these minimally informative things, and sometimes they're expressible in relational algebra. But there are CQ utility views where the minimally informative D views are not CQs themselves. So in particular, you don't know, they're not always the obvious ones, like in the previous example. may be able, if we have time, I can give an example of what can go wrong. We also look within the class of CQ views. Say you're committed that you're going to use CQ views, basic SQL queries with set semantics. For CQ utility queries, you have minimally informative CQ views. And these are almost the obvious ones. After you minimize the utility query, they turn out to be the same as the obvious one. So I'll come back to this a little bit later. But I wanted to say what we were doing in this paper, the perspective was to analyze the trade-offs in view design. You look at questions of the form, are there distributed views that support this query, but which do not reveal any information about this other query? This is what we were interested in here. So back to Simons and Dagstuhl, but making it a little bit more abstract. Simons has a binary relation R. Dagstuhl has S and T binary relations. And I'm interested in supporting the intersection query. Well, obviously, I could support this. I could design sources to answer Q. Each source just exports its data, all of R, all of S, all of T. But I want to know, well, is there some way to do this while keeping the query there exists X, R, X, X private? We analyze this for several notions of privacy, but one notion of privacy would be on no instance should the attacker should the external party know whether there exists X, R, X, X is true. It's sort of a negative version of privacy that has been in the database theory literature. I think it goes back to Mendelssohn and a student. So intuitively, any views that support Q must disclose P on some instance. And okay, it's actually not so, this example with no integrity constraints is not so difficult, but using the prior results, we can compute the minimal information views, show that the minimal information views disclose this thing, and therefore nothing you can do that supports Q. There's nothing you can do that can support Q, but make P a secret. That's a simple case. We also, well, we have several examples where the privacy utility query is less trivial. Here's one of them. We look at the case where there's partial synchronization mechanisms. We look mostly at replication as a synchronization mechanism. Now Simons and Dagstuhl are not completely autonomous. There's a relation S. The relation S that is in the query is replicated between Simons and Dagstuhl. But nothing else, there's no other mechanism. So obviously they need to communicate as data updates come in order to do this. And we have the same utility query. And now we ask the same question, can we support this query while keeping this, there exists XRX private? And the answer now turns out to be yes, there is, well, I'll put this, an interface mechanism, actually a view of a certain sort that can achieve this trade-off. It can support Q while keeping P completely secret. So this is just meant like what were we trying to do and what kinds of results we have. We actually have a general result about what you can do with certain kinds of replication in managing these trade-offs between utility and secrecy. So what is the moral I wanted to give? Well, first, it's not really an answer, but it's my attempt at an answer. We were getting at the idea of comparing the expressiveness of different interface mechanisms. So in this case, it was what can you do with a CQ view versus what can you do with relational algebra views? What can you do with arbitrary functions? I thought this is something that is an interesting direction that I haven't seen much of. And you could look at the same thing with more interactive mechanisms. We didn't do it, but it was an obvious thing is, well, suppose you have access methods, for instance. You can now you can interactively ask multiple queries. Can you achieve these other kinds of trade-offs? And then the second thing I want to highlight is this notion of information theoretic determinacy, the database theorists, information theory. This has been used, certainly by a number of people. Paris and Dan and other people at Washington used it in the query pricing work. I've used it, in many papers, but particularly on information disclosure with Balder and Pierre, other people, also KR people at Oxford. I think also Daniel Kiefer in some of his work uses this. But I don't think it's really been developed rigorously and uniformly. Here you have some information lattice on views. That's the idea in actually in the pricing work and in our work. And you can begin to explore this. So I'll come back to this in a little bit, but I want to talk now a little bit about what's the idea behind this other work about indistinguishability this year. And it's motivated, okay, so first, an indistinguishability relation is just an equivalence relation on databases. I say, here's the pairs of databases that are equivalent. And this gives an interface. Somebody is interacting with the database. What is the queries they could answer? Well, there's two possible semantics. One is that they can answer any query using the certain answer semantics, and the certain answer semantics would be, well, what they're really seeing is the entire equivalence class of this database, and they get the intersection of the answers of that database. There's another semantics which says, oh, it's the answerability semantics. They can only ask queries where the answer is invariant under this equivalence relation. So this would be more like what's called feasibility in access patterns, or answerability in views. So the main point is you have some way of specifying an equivalence relation. I'll talk about some ways you could specify an equivalence relation. That's giving you an interface. And it's interesting in that it's a way of giving an interface that's different from what we're used to. Okay, you can of course think of this as a view. A view, I said from this general mathematical point of view, it's a function on the instance or the local instance that exports some stuff. And you can say, what I'm exporting is the equivalence class. But of course, we're representing it differently. Let's give you an example. I can say G and G prime are indistinguishable if they have the same triangles. These are two graph databases. I can say for all x1, x2, x3, they're a triangle in database G if and only if they're a triangle in G prime. Okay. And this, that's an equivalence relation. It's actually a first-order indistinguishability relation. It's given by a first-order sentence in the language of two copies of the schema. So it's first-order, not in the sense of that we usually say. Now, if you take a typical first-order sentence in the language of two schemas, it's not going to define an equivalence relation. This is a semantic property. These things for all x1, x2, x3, and if and only if between G and G prime, that's going to be an equivalence relation, but other things are not. So I'm interested in the first order sentences in two schemas that will do this. And I can generalize, well, the triangle example is one of them. You give me any relational algebra views, they give a first order indistinguishability relation, the same kind of thing. Well, one database satisfies the views. For every tuple in the union of the databases, it's in the view result in one, if and only if it's in the view result in the other. I'm using this prime notation, just like the G and G prime, to say the prime copy of the database agrees with the unprimed copy on this derived data.
Michael?
Yeah.
The universal quantifiers, are they quantifying over which domain?
They're quantifying over the union of the active domains. So this came up in the prior work. I said these minimally informative D-views exist for arbitrary utility queries. And how do they work? Actually, the way we can present them is as an indistinguishability relation. Obviously, we can show that you can't always get, in very natural cases, you can't get relational algebra, but you can always get this indistinguishability relation presentation. Actually, I think in a second order indistinguishability relation. And then there was this example I talked about with replication. I said, well, we could support Q without revealing P. How did we do this? We needed some interface mechanism beyond relational algebra views. We could show that you couldn't use any generic query to do this, but we define a simple indistinguishability relation that actually looks at the data values. And we show that's the way you can achieve this trade-off. So you can achieve certain trade-offs with indistinguishability that you can't achieve with traditional views. Okay, this is a super general notion. We study this mostly over infinite structures, focusing on first order and infinitary logic. But there are a few results that I can mention that apply to the finite case, to finite models, to databases. I said that traditional relational algebra views give a first-order indistinguishability relation, and you can ask, well, what are the other first-order indistinguishability relations? Well, nested relational calculus gives you another class of first order indistinguishability relations. I don't want to explain what nested data is, or nested relational calculus, but I'll explain by example. If I have a binary relation, RXY, I want to export all the adjacency sets of elements in my database. This is a set of sets. For every element, I take the set of things that are adjacent to it. And then I take the set of sets by varying the X. Well, that's a set of sets. I can say two databases agree on this set of sets in first order logic in this dual signature, the R and R prime signature. It's for all X, there exists X prime. For every node in one, there's a node in the other database whose adjacency set agrees. So in general, okay, I can do sets of sets of sets the same way. That's the general idea of nested relational calculus. I build up these sets of sets of sets. You know, it's a different query language, and agreement on a nested relational calculus query gives you a first order equivalence. So let me jump, since I'm running low on time, to the open question here. We have various results about this, but an intriguing open question is every first order indistinguishability relation given by a nested relational calculus? We look at the infinite case where this is not true, and we find lots of phenomena that go beyond nested relational calculus. And of course, we don't use the word nested relational calculus because it's geared towards a different audience. This is a preservation question. I have a first order sentence in the language of two schemas. I impose some semantic property. Here's a syntax, nested relational calculus views that enforces it. I want to know if everything that has this semantic property is enforced by this syntax. Okay, so first I'll say the bottom line, this indistinguishability relations, they make the world of traditional views look very small, because you can begin to see lots of other ways of creating interfaces that are beyond views. And it gets at this issue that comes up often in descriptive complexity theory and descriptive set theory, of going from an equivalence relation to a canonical representative. For instance, if you look at various notions of elementary equivalence, like n-variable equivalence, you have a nicely described equivalence relation. You want to know how efficient it is to export a representative of this equivalence relation. You have a nice representation of sort of the dynamic notion. You want to know, does that mean that there's a nice representative? You can choose a representative concisely. So I want to stop now with the great thoughts stuff, if you could give me a second to do it. Okay, so I want to go back to great thoughts. And the truth of it is, I saw Mulham's talk last week, and he gave an overview of relational databases, and it led to some great pronouncement. Relational AI is great by relational AI, and other profound thoughts. And then I saw Joe's talk, and he overviewed relational databases for 15 years, and he gave his own pronouncements, morals. I love Hasselt, and there's important problems with synchronization that need to be studied, and Daedalus is great. And I thought I should have a slide that talks about 50 years of databases and then has some profound conclusions. I couldn't, what I want to say is, well, in the first 40 years, this notion of logical interface, expanding it, and notions of comparing interfaces, you find it relatively often in PODS. There's Rick Hull did some various things about the notion of information capacity that I find very interesting at the level of comparing schemas. And then, of course, there's been a lot of work over 40 years at looking at funky new ways of defining interfaces. But in the last, I'd say, certainly 5 years, not so much. So I think there is some need to look at this. I wouldn't say, looking at the work in this workshop, I don't say that people should stop working on machine learning and relational algebra like Zach is and look about this. A little bit maybe goes a long way, and maybe there was too much of this at one point. But I think going back every few years and looking at this is a good thing to do. Certainly this work has been very influential outside of databases. Thank you.
We have one question and then switch off the recording. Sudeepa?
Due to connection with differential privacy, if you are trying to hide information from one view, you mentioned Daniel Kiefer's works. So has anyone looked into that?
So we haven't looked in this. I think this model is just I've shown this stuff to some people who work on privacy, say this is ridiculously restrictive, which I think is the right answer. I mean, our notion of that I showed you of keeping something secret is on no instance should the attacker learn the database, which is something that comes in the database theory literature. Also, it's in the KR literature, but of course, it's in the end, differential privacy is much weaker. You said that, and in general, the reaction is, look, I don't care that there's one database out there in the world.
It's mostly used for aggregate queries. So if you have views like non-aggregated views, so the notion is not obvious, but yeah.
Yeah, so first of all, very interesting. So I got your framework and the results. It look amazing. Quick question.
I didn't get a chance to do justice to the indistinguishability results, but I can tell you that it's not important.
But can you do justice to communication complexity? Have you looked into this?
Yeah, I mean, so no, well, not really. I mean, the proofs have a very similar feel to communication, that we're exploiting autonomy of this. And you would think once we put in some interaction between the two sources, we're an extreme case of communication complexity, I'd say, because there's no communication between the sources at all.
Well, they both publish something in common, so they can compute a view. Maybe it's a one round, half round, I don't know. They looked at all sorts of variations, which I'm not familiar with.
Yeah, it's on my radar to look at, but I didn't look at this.
Yeah.
So like I had a similar question to Sudeepa, right? But right, so like yes, it's a differential privacy is a weaker model because we only have probabilistic guarantees, right? But your model is also in another way more expressive, right? This indistinguishability relations allow me, right? Differential privacy is essentially like a very simple, and if you want to distinguishability.
But there's still no probabilities involved, even in the indistinguishability notion, right?
No, I know, right? I mean, like, right, your model is not just stricter, but also more expressive in what we consider to be indistinguishable, right?
Yeah. But I'm mangling two works, right? So on the one hand, you have this notion of privacy that we give. On the other hand, we can be flexible about the view mechanisms and look at these more powerful mechanisms, right? So that's true. Some of it, I just want to make clear that some of this trade-off is in two different works, but go ahead.
Yes, agree, right? So I know that indistinguishability was basically like a query language for us to define views, right?
Yeah.
But it could also be obviously used for like a privacy mechanism.
Yeah. Remember, I said that I won't be ready for great thoughts till tomorrow afternoon, or possibly Monday, or maybe next week.
Yeah. So can you comment a bit about the complexity of computing these views? Because terminus is undecidable, right? It's so rather very easy, and you can just compute them.
You can just, so in the case of CQ utility queries, you don't need to decide determinacy. You can get these minimal information views, and actually in p-time you can create.
For other queries?
Well, for other queries, we don't actually know what the representation is. So Pierre, do you want to contradict? Okay, so actually, well, I mean, okay, so you can get relational algebra views without doing minimization, Pierre.
Yeah, but
if you want to get the C, so it depends what format you want the views in. You can, yeah. Yeah, no, you do get the minimal one. You just don't have it as a CQ. So it depends on what represent. I mean, if I've understood your comment correctly, there's two results. One, it says, okay, I can get these relational algebra views, and there we use this construction about getting these shuffles. And I think you can do this in p-time. It is minimal in information. It's just, if you want to, there's another result that says I can get CQ views, and there I need to minimize the global word, which, as Peter said, is expensive. But then, after you get these minimal views, you have to see whether you can do disclosure. And there we have some results on this for the case without constraints. We know how to do it. I mean, we know there you just look at the minimal, at this canonical instance. And then with constraints, I don't remember whether we have complexity bounds for this yet.
We have some abstract constraints like guarded constraints.